Welcome DIKWP Sogong aboard. Your learning journey starts now. Ever wondered if your AI agent is just a fancy collection of numbers? Or does it have something more, something that survives even when you swap out its brain? Let's dive into the heart of this mystery. So, Muse Glimmer comes along, flexes its muscles on some benchmarks, apparently beating Quen. Sounds like a slam dunk, right? Hold your horses, look closer. On MCP Atlas, Muse leads by a whopping 13 points. But flip the coin, Quen absolutely crushes it on O's world, leaving Muse in the dust with a negative 9.7 gap. What's going on here? It's not about the models themselves in isolation. These scores are snapshots of specific worlds, unique tools, prompts, and judges. Benchmarking tells you how well the whole package works in that specific sandbox, not some universal truth about the model's soul. It's like judging a chef only by how they cook one dish. The real story is far more complex. Now let's talk size and speed. Meta squeezes Muse down to under 20 gigabytes using 4-bit quantization. That's huge. They claim only a tiny average drop in accuracy, maybe 1%. And D-Flash makes things fly, promising up to 3.1 times faster decoding. Sounds great, right? Faster, smaller, almost as smart. But here's the catch. Averages can be misleading. An average 1% loss doesn't mean every single critical action loses just 1% precision. What if a rare high-stakes protected action gets subtly altered or split between the original and quantized versions? Your agent might still pass most tests but fail spectacularly on that one crucial task. The weights got smaller, but did the identity survive the compression? Not necessarily. Okay, so we have these powerful local agents doing complex tasks. What happens when things go wrong? Like, really go wrong. Imagine your agent tells a tool to deploy a critical update, but the response times out. Does the agent just assume it failed and try again? Big mistake. This is the ambiguous commit problem. If the first action actually happened, a blind retry isn't healing. It's creating chaos, duplicate payments, double deployments, irreversible messes. The solution isn't just trying harder, it's smarter recovery. You need to check the status first. Did it really fail? Is the action idempotent? Doing it twice is the same as once. Can you compensate for the error? This is audited self-healing, making sure repairs are actually repairs, not just repeated mistakes. So how do we build agents that truly persist through changes? Enter DIKWP RemainderOS. Forget thinking the model weights hold the identity. The real essence, the purpose, authority, obligations, data custody, repair history, lives in the protected future equivalence class. Think of it as a control plane sitting above the replaceable model kernel. It uses concepts like action passports for each tool call, keeps an immutable log of everything, and enforces strict rules for recovery. This means you can swap out the model, maybe switching from Muse to Quen based on the task, and the agent's core identity and continuity remain intact. It's about building systems where the agent's soul isn't tied to its specific brain, but to the ongoing work and responsibilities it manages. That's the future.